Okay, so we're going to talk now about a generalization of the lottery problem from the previous. In the lottery problem, we assume we had some number of balls labeled distinctly. So we just assume we had 52 balls labeled 1 through 52, and we were going to pick 6 of them. Put them on a lottery ticket. And then the prizes are determined by how many of the balls that were chosen actually match our lottery ticket. This is a special case of what's called the hypergeometric distribution. Hypergeometric distribution is a distribution for choosing balls uniformly at random without replacement. Okay? And so the setup is as follows. We have an urn. This is what's called an urn model in probability. So urns are pretty maybe antiquated, but you think of an urn, it's just a big box. And the urn contains n balls. And each ball has one of two categories. G are good. And B, but we define B as n minus G, are bad. So good balls and bad balls. We're going to choose little n less than big N. Balls are chosen at random without replacement. So now for a given draw, we're going to let capital X be the number of good balls drawn. Without replacement. So let's emphasize that. Okay. So now what we want to do is we want to calculate, okay, what is the probability that X is equal to little r for each of the possible values of little r. So out of little n draws, we have capital N balls. There's a chance that we have 0 draws up that are good, upwards of little n that are good. Okay. So we can just generalize the lottery example from before. We can do either analysis. In the ordered analysis, probability that X is equal to R. Okay, how did we do it? First, we said, okay, well, there's little n slots that we need to put R good balls in. We have capital G good balls, and we need an R permutation of those, G fall R. And then of the remaining bad balls, which is capital N minus capital G, we need to get a n minus little r permutation of those. And then how many possible orderings are there? There are capital N, ball, little n. Okay. In the unordered analysis, probability X equals R. Now what we need to do is we say, well, we're going to be picking little n balls. We want R of them to be good. We want little n minus R of them to be bad. So it doesn't matter what order. So we take G balls. We have to pick R of them. We take n minus G balls. And we have to pick little n minus R of them. And how many possible unordered ways to pick little n from n? Well, let's let capital N choose little n. Both give you the same answer, and you should verify that these probabilities are exactly the same. It's just a different way of thinking, different way of coming up with the answer. Okay. So verify that these are the same. Some things to note here. First is that the probability that X is equal to R is 0 unless the maximum, let's write down the condition and then see what we mean. So R cannot be greater than the minimum of N and G. Why? Well, suppose R was greater than G, then here we'd be asking to pick more good balls than there are good balls. Can't choose 10 things out of 8, right? And if R was bigger than little n, then we'd be trying to choose a negative number of bad balls, which you can't do either. So that explains this upper bound. Now let's suppose that R, of course, was less than 0. You can't choose less than 0 balls from R here. And if R is less than n plus G minus n, we'd be picking more than the number of bad balls. So we'd be asking for more bad balls than there are bad balls, and that wouldn't work either. So that's where those conditions come from. And the distribution takes care of it for us because n choose k, where k is bigger than n, is 0. So the probability will automatically be 0. So the second is the number of good balls drawn, and we've written that as X, is a random quantity that follows the hypergeometric distribution with parameter capital N, capital G, lowercase n. We're going to talk about this in more detail later on in the course. These are the 3 parameters. So this is what you need. You need these 3 parameters. You need to know how many balls are there, how many of those balls are good, how many balls are you going to draw. If you know how many balls there are and how many are good, then you know how many bad balls there are. So you don't need to specify that explicitly. So that's the hypergeometric distribution. And we'll be talking about this more throughout the course. That's our first distribution in this course. Okay. Let's continue. When we come back, we're going to continue with a well-known problem called the birthday problem. We'll do that next.